So, in the grand scheme of things, this might be useful just to kind of recap in terms of the big picture. We've really been talking about finite elements. Method was developed in the late 1950s, primarily to deal with solid mechanics problems. But we chose to not talk about solid mechanics problems initially because they were a bit more tricky, even though the method is still uniform for all the different techniques, all the different physical problems we'll deal with. But when we talked about solid mechanics, we no longer deal with a scalar variable. We have a vectoral variable in terms of displacements that we have to deal with. So we chose to introduce things first in terms of a second order PDE, which accounts for fluid flow and pressure diffusion, the groundwater equations, I guess. And this is really a blunt instrument right now. It's be quite, which is interesting actually. Why is it so blunt? That's really blunt. Oh, I guess these are ones as well. And so we talked about this. So this is in terms of something that looks like d2p dx squared k over mu, if it was written in petroleum style, compressibility, change in pressure with time. And so we noted the fact that the variable is pressure or head in these cases. It is scalar. There's a second order PDE that we have to deal with for the flow part. And if we deal with transient behavior, we have this capacitance term. And we talked about how we would deal with that in the first place. We extended then that. I guess we noted the fact that because we're dealing with this second order PDE, the system of equations end up being written something like Kp plus Sp dot equals flow rate, where these are individual matrices. And we made the case that these second order terms that operate on the pressure always have the same form in the finite element statement, that they are something like A transpose dA integrated over the volume, where this matrix is something that links, in this particular case, velocities to gradients of pore pressure, which we call P comma or H comma. So this is Darcy's law, constitutive equation. And the A matrix was something that linked values of pressure magnitudes or head magnitudes to gradients of those, dp dx. And so these were the derivatives of the shape functions. And that was always the case. If we looked at the first order or the zeroth order term, then this was always just a collection of shape functions for our system that defines behavior. And this would always be the case for these systems. This would be a second order. This is a zeroth order. And so that was useful in defining the behavior of our system for flow problems. If we looked at transport problems, either in terms of dissolved components as mass transport or as in thermal transport, then we typically had an extra term to deal with. And that extra term would make up a PDE that looked something like a capacitance term, say concentration with time being operated on by something that could be 1 but could be different from 1, and a part that looked like a diffusive term, just like the diffusion of pressure that we had before, and also a term that operated on a velocity and a rate of change of concentration in space, which is a first order PDE. And in that particular case, if we wrote out the system equations, they would look exactly like this, just by rearranging them. And this diffusive term would be the same as our second order term that we talked about in terms of pressure diffusion, but this advective term would be the one that would represent this. And this advective conductance matrix would look something like integral, is it B transpose times velocity times the derivatives of the shape functions over the volume of the element. And this would be the same as the shape function terms here, which I guess we didn't define, but I guess it might be worthwhile defining. We know that the shape function terms just map, for instance, pressure at the nodes multiplied by the shape functions gives us the pressure at a particular point in the element, any point in the element. And so this would be the part that goes in here. So shape functions, the derivatives of the shape functions, and some constitutive matrix. And so we don't need anything more than that to be able to define these. Here, these are the derivatives of the shape functions, and these are the shape functions themselves. And this is just the magnitudes of the velocities in the element. And so even though the finite element method was developed for the displacement method of structures, we avoided dealing with that because in all the cases that we've talked about so far, the two cases, in talking about transport of dissolved components or transport of a pressure pulse, it's diffusion of the pressure pulse, not diffusion of anything else. These were indeed, the pressure is a scalar value and also concentration is a scalar value, as indeed would be temperature if we wrote that. And so we avoided dealing with that. So the stuff that you would have looked at online would have talked about applying this now to a new set of equations. I don't know that in the recording it ever talked about the full set, but the system of equations would look rather similar to something like this, that has a term that operates on the variable itself, which would be displacement, the time derivative of the variable, and maybe in this particular case also the time derivative of the time derivative, which would be, in the case of displacement, this would be displacement, this would be time derivative of displacement, which is a velocity, and the time derivative of the time derivative of displacement would be an acceleration. And so the system of equations for solid mechanics, even though it was probably not written this way, would be something like applied forces as a vector would be equal to a stiffness matrix times a displacement plus a damping term multiplied by a rate of change of displacement plus a mass term multiplied by a rate of an acceleration, u double dot. So this, of course, not of course, but is d2u dt squared. And it would be in x direction or y direction, whichever. It's a vectoral quantity. The reason for dealing with this way would be that if you think about this in terms of Newton's law and draw this out here, this would basically be F equals ma. So this is the inertial term. We won't deal with anything that includes that. We'll just deal with the only part we're interested in will be this, the steady state part. The non-inertial and steady state part. It is steady state, not changing with time. And so we'll only deal with this left-hand portion, in which we need to know something about the stiffness matrix. And just to recap, the stiffness matrix, because this term here is representing a second-order PDE, the stiffness matrix is actually the integral over A transpose dA, something you've definitely seen before. This is Hooke's law. And the A matrices are just the derivatives of the shape functions for the particular elements that we choose as well. And so there's some similarity between all of these components because it's a second order PDE, even though it's operating on a displacement which has directions of magnitudes in both, I guess, x, y, and z. If you look at the right-hand coordinate system, then this matrix looks a little different because it'll have more components than the ones that we had that operated merely on a scalar value. But we could put it together in the same way as we did for Navier-Stokes flow, if you recall, where we actually looked at flow velocities in two different directions for triangular elements and pulled the matrix system together just by heuristics, I guess I would say. So that's where we are. So we're interested in being able to deal with this. And so I think when this was dealt with, this equation here was introduced by the principle of virtual work, which basically says that you can sum up, I always use this as an illustration, is that you can sum up the amount of work that you do on something. So if you know what force you apply to this to deform it, then the force that you apply on one end of this object is a force that's applied, and as it compresses, it'll go through to some displacement. And so the work, the external virtual work you do, so if you I just draw this out here. If I push here with some force, and it goes through some displacement in shortening this, which is delta U, then the work, which is force times distance, is equal to F times delta U. So that has to be balanced with what's going on inside this. And so what's going on inside this is it's shortening by some amount. And so this force is applied as a point force, and it goes through a finite deformation delta U. But what it would do is to every single point within this structure, there would be some strain that would be applied, and there would be a stress that was a result also of this same force which is moving in the boundary. And so the external work, you could imagine, is just the force that's applied times the displacement. The internal work is just going to be equal to the product of the equivalent of force would be a stress, and the equivalent of the displacement would be a strain. These are actually vectors, and it's the product of these two which are equal to each other. And so the principle of, the displacement equations for structures, which were developed in the late 1950s, were based on exactly this principle of virtual work. And it allows you basically to get this relationship F equals KU, which we've used. And so historically, that's kind of an interesting aside. So we've done things a little bit backwards historically in terms of we've introduced those behaviors specifically for scalar variables. And now, only now are we introducing the magnitudes for the non-scalar variables. I guess we did it for Navier-Stokes flow as well. But basically, we're in the place to be able to, we've covered both of these. So what principle virtual work gives us is the ability to be able to get this, which is the expression that defines the stiffness matrix. We've called all of these matrices K because they've been referred to as stiffness matrices for a one-dimensional element, for a triangular element, and then we've talked about different forms of the constitutive equations. And the different forms of the constitutive equations are merely the fact that when we talked about flow problems, what we could do was just, if it's flow just within a plane, we could ignore the flow in the orthogonal direction just by putting the conductivity for that equal to 0, basically, because there's no gradient in that direction. But if we do that for solid mechanics problems, we have two behaviors to be able to accommodate. One is where the displacements in the plane perpendicular for a two-dimensional problem are 0. In other words, if you can imagine all of these lamina, such as for a dam, repeating themselves. So you take a two-dimensional cross-section of a dam that goes an infinite length into the page, then a single lamina of that the boundary conditions are that it can't expand itself relative to the sheet that's next door to it, because that sheet is trying to expand at the same time. And so if you're applying a load, say along the top of this structure, then that load is affecting every single of these laminae, and they're all trying to expand laterally. And so the appropriate condition there is that the strain in that third direction, whatever we call it, Z, I guess, is equal to 0, which is the condition of plane strain. And the converse is that if you take something which would be a very thin sample and loaded it, such as this, which only has maybe an inch in this direction, and load it, then clearly there's no restriction on it straining laterally. And but what is happening in this is that there's no stress that's applied in the orthogonal direction. So the other condition is for the change in stress in that direction is equal to 0. I guess it would be a change in these cases, which is plane stress. And so these considerations modify the form of the constitutive matrix. And so that has to be accommodated. So that was really the message from last time. So that in terms of the mechanisms that we've talked about. So when we introduced this class, we made the point that we're talking about these coupled processes in terms of THMC, as it's often referred to. So THMC refers to the different fields that we're interested in. And so C is for chemical behavior, transport, and reaction. M is for mechanical. H is for hydrologic. And T is for thermal. And so hopefully you'll note that these are exactly the 4 suites of behavior that we've looked at. We looked at hydrologic behavior first with an expression that is something like SH dot plus KH equals Q, if we write these in expressions. And so the head, or pressure, we prefer to work in pressure actually, is the dependent variable that defines this. For mechanical behavior, we have a system of equations that is something like F equals KU, where this is forces that are applied, displacements that result, and they're modulated by a stiffness matrix, which we've spent some time talking about here. Chemical transport, the relationship is something like, we've just drawn it on the previous, it's something like storage times rate of change of concentration plus a conductance matrix for diffusion and a conductance matrix for advection, which operate on concentrations, and these are equal to mass flow rates, fluxes. And so this, if you've just screwed up this page to where we've come from, you'd find that equation exactly here. So it's no different from that right here. I guess they'll both fit on at the same time. And for thermal, it would be actually equivalent. And so it would be something like capacitance, but now of a rate of change of temperature, plus a conductance term, plus an advective term, both operating on temperatures, is equal to a thermal flux. These are all matrices and vectors, matrix and vectors. And so actually that's in a pretty compact way, that is exactly the system that we have attempted to represent. And so we dealt with this one first. I think we dealt with this one second. We barely touched on this, but it's the same exact set of equations that influence chemical behavior. And the last one we dealt with was mechanical behavior. So that was the sequence. So what we'd like to do with that now is to think about how we can combine those behaviors. And so you could imagine coupling them in a variety of different ways. The first coupling that we do today isn't really coupling at all, but it's maybe a useful run-in to be able to talk about these behaviors. But if you wanted to, you could take each, you could look at permutations and combinations of these different behaviors. And so we could divide this quadruplet behavior, so these four different terms that might interact with each other, you could look at subsets of them. So we could look at hydromechanical behavior, we could look at thermomechanical behavior, etc. And we could look at all the different combinations. And so we can choose that based on what we're attempting to do. But what it might be useful to do is first is just to talk about this, what we've developed so far, in terms of this matrix, which we've never really used. And so let me, so first of all, remember what we've talked about here. We've talked about a variety of different expressions which on their own are completely independent. So we could solve the heat flow problem just by solving a mesh with appropriate boundary conditions and with temperatures applied, and look at the propagation of temperatures within that system, and it wouldn't have any influence on anything else. It wouldn't change stresses at all. We could look in the same system by looking at the mechanical behavior, and if the information about the thermal stresses was not sent or parsed to the mechanical expression, then there would be no net influence. And so what we're attempting to do now, I'm not sure where the first occasion of that one figure that I want is going to be. It doesn't even matter where it is. I could draw it out perhaps just as easily. Why don't I draw it out? Just because I can. Would it be this? Yes. Right. So that's what I'm going to do. Right. So you'll remember something that looks like, in terms of our dependent variables. Let's see how well I can draw this. And so you'll recognize this as soon as I get part of it down, even though it's a bit scrappy. So it's going to have 4 rows, and I'm not sure what sequence we drew them in, but I'll talk about displacements. I'll talk about, and then in the sequence we introduce the pressures, concentrations, and temperatures. And we have another set of expressions. Again, not a very well drawn bracket, but these operate on rates of changes of displacement, rates of changes of pressures, rates of changes of concentrations, and rates of changes of temperatures. So they exactly mirror these prior components, and they operate on some terms. Let's figure out exactly what those terms are. So each of these relationships, not obviously, but have a 4x4 matrix that operates on it. And so I'll do this. And so you can perhaps imagine that if I change the color for a second, that if we look at solid mechanics, ignore the fact that we made the case that there should be these terms. So F equals ma suggested that the relationship that we might want to deal with would be something that would be force is equal to a stiffness times a displacement plus a damping term times a velocity plus a mass matrix multiplied by a acceleration. I don't think I said so at the time, but I'll say now is that this mass matrix here would actually be the same as the storage matrix. So it would be a density multiplied by the integral B transposed B dV, this M matrix. And that makes sense if you think about it. Remember, we spent a bit of time talking about what this matrix is. What it does is it distributes the volume somehow between the ends of the nodal values. If you add all the terms together, then the concatenated terms that exist in this is just equal to this. This is equal to just the volume of the element. So this is the volume of the element. So multiplying the volume of the element by the density of the element is its mass, right? So if you're shaking it, this is the inertial resistance. We'll only deal with the steady state part, the non-inertial part. And so if we were to write this out, then this would be, we would call this K solid mechanics. So this would be Ks. And it operates on displacements, and there are no terms that operate on damping because we're going to ignore it, and there is no way to incorporate the acceleration term in this. If we look at the flow part, I don't want that. I'm going to do something different color. So flow would be, so I guess solid mechanics part would be the M term. The flow part would be the hydrology term for H. We've often written it in terms of heads because it's convenient, but it's actually much more convenient to write it in terms of pressures because it's pressures that influence deformations rather than heads. It's much easier to write those expressions in terms of Terzagh's effective stress wall, which we haven't introduced yet. And so this will look something like, what is it? It's going to be storage times rate of change of pressure plus hydraulic conductivity times, conductance matrix times pressure equals flow rate. And maybe we should put an H on this to represent the fact that it's the flow part. And so if we did this, then clearly this part goes here. Clearly this part goes here. And this remaining part would go here. I guess we didn't finish off the top one. This is, yes. All right, okay. Yeah. So we mentioned before that we could write this expression here, in which case this term would go in here. But the other thing that we could do, and it turns out to be advantageous for us to do it, and that is that we could also write this expression here as taking the derivative of each side. So we'll ignore this on both sides. But if we take the time derivative of displacements and the time derivative of forces, then instead of writing it exactly where it's written now in terms of this displacement, it could be written in terms of rate of change of displacement. And if we did that, then we'd take this and we'd move it from here. This is the only one that was my mistake. I wasn't thinking very well. And we'd write it here. So this is K M, I guess. And then this would be F dot. So mechanical behavior, hydraulic behavior, contaminant transport part, maybe different color, mass transport, and it's going to be the same, or it's going to be very similar. So maybe this should be a capacitance matrix. I suppose we should give it some unique term. Let's do it C for contaminant transport multiplied by concentration plus these two other matrices, which are conductance, a diffusion matrix if you like, and an advection matrix operating on concentration, and that's equal to QC, for want of a better term. And so if we were to put this into the right locations in here, this term here would operate on concentration. These terms here would operate on rate of change of concentration, rather. These terms here would operate on concentration, which would be K sub D plus the advective term together. And this would be a flux. These are rates of change, right? A flux is a mass per unit time. This is a force per unit time. This is a volumetric flow rate per unit time. So these are rates of change, all of these, just that it doesn't have a circumscribed dot because of the way we describe it. And I guess finally temperature, I don't know if there's another, yeah, it's fine. Temperature, heat transfer or heat transport is going to be the same. So a storage term, which is rate of change of temperature, plus both a conductive term and a advective term, convective or advective term, operating on temperature, is equal to thermal flux. And so in the same way as before, these are directly correspond. And so this is the term that would go here. And this second term here would go here. K advective and K diffusive and K advective together. And it's just consistent. These are vectors, so they're underlined, so they should, everything here should be underlined, and they would operate on magnitudes of thermal flux. And so that is, well, that's our ultimate goal in this. It's part of the picture, but not all of it. Because all of the terms that we've put into this relationship, they all exist on the leading diagonal, they have absolutely no interaction with each other. And so if you, for instance, change the temperature, that's fine. Then this bottom equation here will say how the temperature will change in your structure as a function of time if you apply appropriate boundary conditions. But the temperatures that you have no influence on any of these other equations. The temperature is always in the bottom column here, so it always refers to, this would be temperature, this would be temperature rate, Just can get these colors right. This would be concentration, rate, and this would be concentration. This would be pressure and pressure rate. And this would be displacement, rate, and displacement. So right now, because there are no terms in this column here, then a change in temperature that results won't have any influence on any of these other equations. And so that's the reality of it. And so our challenge would be that if we want to, for instance, represent the simplest of these couplings, and one simple coupling would be thermomechanical behavior. So the very simple idea, right? So thermomechanical behavior is not for board duster, but if you heat this up, it gets bigger. That's fine. Nothing changes. The stress doesn't change, but the strain would change because it would physically expand. If you heat it up and you hold it and force it to not expand, then it'll build up stresses in it, and you can calculate what those stresses would be from the coefficient of thermal expansion and the modulus of elasticity of it. And so the mechanical interaction for those boundary conditions would be that you'd want to, if temperatures change, you'd want to be able to affect the magnitudes that influence this top equation to figure out what the stresses are. So in other words, what you'd expect would be that there would be some term that exists here that would allow you to be able to calculate from the temperature, magnitude of temperature change, what the influence would be on the force that exists in this equation. So that would be one potential term that would exist. The other potential term would be that since we're looking at thermomechanical behavior, then it affects the equation F equals Ku, which is the solid mechanics part, and it affects Q equals KT, which is the steady state thermal conduction part, which is really what this term really is. So you can imagine that to be able to have some influence, you have to have terms in these off-diagonal locations. The other off-diagonal location that links both displacements and temperatures would be this one. And I suppose you could make the argument that it could be here as well, right? Because these are the time derivatives of those influences. And so how rates of changes of those affect it. And so I'm not sure, I haven't thought about these ones, but this one would be what? This would say that if you had some influence on displacement, then there would be some change in temperature that results from this, heat flux that results from this. So this term here would be the effect of taking this, doing some work on it, and measuring how the temperature changes as a result of the work that you do on it. You can imagine if you put work into it, it should change temperature in by some magnitude. And so that's what this term would be. This term would be, if you change the temperature, what happens to the displacements. The other thing perhaps to realize in thinking about this is that all of these equations, as you go along the horizontal here, these equations have to be they all have to be apples or they all have to be oranges together, right? They have to be the same units. And so if you look at the expression for any one of these, I'm not sure what the easiest one would be. I guess this would be, the easiest one I guess is the first one because it's just these two terms. All of the terms that exist in this, the units of this term here have to be units of rate of change of force, right? Because this is a force that's applied, it equals stiffness times the displacement, but the product of these together have to be the same units. And so all the expressions in this horizontal equation have to be the same units, and they have to be units of rates of change of forces. All the expressions on the second term have to be a rate of change. So this is newtons per second, I suppose. This is a volumetric flux, so this would be meters cubed per second. This is a concentration, a mass flux, so it would be, say, kilograms per second. And this would be a heat flux, so it would be watts, I guess. Yeah, watts per second. So a watt is a watt. What's a watt? Interestingly enough, I was just in, it wasn't Watt from Glasgow? I was just in Glasgow. Certainly Kelvin was. A watt is a Newton meter per second, or a joule per second. A power, which is a watt. I guess we're going off on a tangent. Power is the rate of doing work. Work is a Newton meter, so rate of doing work is a Newton meter per second, and we call a Newton meter per second a joule per second. Joule is Newton meter, right? So, which is equal to energy per time. Energy or work are the same things, same units. So power is just the rate of doing work, rate of doing energy. So joules are energy, and output is energy divided by time. And so all of the terms that exist in this one equation on the bottom have to be in terms of power, work per second. And so you can think about, it's useful to think about these in broad terms as to what these interactions would mean. The other way to, and we'll deal with this in due course, the other, let me make this smaller so it fits on along, whoops. The other way, the other coupling that we might be interested in would be hydromechanical behavior. And so hydromechanical behavior, again using this analog, is you take a sponge and you fill it with water and you put it in a plastic bag and then you squeeze it. And if you squeeze it, what will happen is the sponge will contract, all the pores in the sponge will get smaller, and it will squeeze the water out. And if it wasn't in a plastic bag, I would get wet because it would go on my leg. If you hold it in a plastic bag and, for instance, put this inside a container that doesn't allow it to expand, then instead of being very compressible and compressing, then if you constrict it in a sheath that doesn't allow it to expand, it'd actually be very stiff because all the fluid that is trapped in there is trying to get out. It can't get out quickly enough because it's constrained, and therefore you're measuring really the compressibility of water, which is basically the same compressibility or stiffness as rocks. You know, compressibility of water is about a couple of gigapascals, and rocks are maybe 10 or 20 gigapascals in terms of their stiffness. And so if we're thinking about hydromechanical behavior, then again, the two systems that we're interested in coupling together would be the same as the first one here, mechanical behavior. It would be the analog to this for flow, which would, I guess, would be this one, which would be Q equals K. We've called it head, but now we're going to switch to start calling it pressure. And it would be the terms that exist in these locations here. And these locations here. For the same reason we said before, is that it operates on displacements and pressures, or rates of displacements and rates of changes of pressure. And so again, without these off-diagonal terms to link it, there's zero coupling. There's no influence of one system on the other, and they just happily behave on their own. But if we attempt to link these systems, then what we need to do is figure out exactly what the coupling matrices are. And so it would be the terms that perhaps go into this location, and this location, and this location, and this location. And it's the ones on the left we don't have to worry about because they don't exist, but the ones on the right do. And so what these would be is that you can think about them, well, maybe it's worthwhile writing it out in longhand. So let's write this out. So if I just take this portion here and write it out in terms of the full system of equations for these first two, it would be something like the stiffness matrix for the mechanical behavior multiplied by u dot plus another term which I'm going to call Sm. Perhaps that's not a very good use of, sorry, not u, which operates on p dot. So all I'm doing is taking the individual components out of here and including this. And then I'm going to do the same to the term underneath it, which is going to be, let's call this S. I call it P because I've already used, unfortunately, this term here. Operating again on U dot plus SP times P dot equals Q. And it's not quite right because we've allowed it to have these two terms, but we haven't included this. And so I guess we need to include another term on this side, which is the conductive part. Hydraulic conduction times fluid pressure. And so this is just a longhand way, if you like, of writing out the terms on the top part of this plus this term. The rest are zeros. And so if we think about what these terms are exactly, then what are they? So this is just the straight mechanical part that allows it to deform without the influence of fluid in it. This is the straight flow part that allows flow to occur and it doesn't care about any deformation. This is the part that is due to the rate of change, the compressibility of the fluid. So you remember that we described what this storage magnitude was. The idea was that the storage is that if you change the pressure at the end of the element, then all of a sudden if you change the pressure, you allow the fluid to expand or contract depending on whether you increase the pressure. And so if you increase the pressure, then the fluid would contract. It would fill up less of the volume of your element, and therefore it'd have to suck amount of fluid in to be able to fill it up. If you drop the pressure, that fluid would expand, and it would just flow out of the system, and you'd have to release that amount out of the system. And so that's what this physical term is that does that. They respond in the top equation. All the terms are written in terms of a rate of change in force, and all the terms here, we call them something, right? KH. This is a mass flux, a volumetric flux. And so the interesting terms then for us to think about are what are these other off-diagonal terms? What do they physically mean? And so what we could do is we could write them on their own, ignoring the other terms. So if we took these, what I'm going to write as the green terms, and we just wrote them on their own without all of these other complicating factors, we'd have one that would say something like this. This one here. And we'd have one that says something like And so pulling these out and ignoring everything else, we can figure out exactly what they mean. We can do this, of course, if there is no change in deformation and pressure is constant, and the pressure doesn't change as a function of time either, which would be the case if pressure is constant both in space and in time. And so the coupling matrix terms that we have here really say that what is the force that's applied if we increase the fluid pressure within the system. That's really what this term is here. So if you change the fluid pressure, what is the force that's applied on the porous medium as a function of that change in pressure? And the easiest way to think about this is that actually, no, this is, yeah. The easier one to think of first is this one. This is very straightforward, right? This is basically saying that we have a set volume, and what we're going to do with that set volume is we're going to compress it. We're going to compress it at some rate, and it's going to get smaller. And if the pressure doesn't change, because it's squeezing, the only way that pressure can't change if it's allowing the fluid to squeeze out of it. And so basically this is a relationship that's saying we're compressing this at some volumetric compression rate, and the amount of fluid that comes out of it is exactly equal to that volumetric compression rate. It's nothing more than that. So the physical definition of what's going on is basically that. So this is just the volume change of the fluid being squeezed out is equal to the volume change of the boundaries of the element as it compresses. So that's the easier one to define. This one is saying that as you change the fluid pressure, then the total forces that you're applying to the system are changing because the fluid pressure is acting against them, basically. And it turns out that these two terms on across the diagonal are they're symmetric. They're the transpose of each other. They turn out just to be symmetric, which is kind of a mathematical curiosity as much as anything else. So yeah, so those are the couplings that we will deal with. So that's kind of the essence of what we're going to attempt to do. I was going to talk about some other things today in applying it to dual porosity behavior, which isn't quite the same coupling as this, but I don't think we'll go all the way there today. But we can play some games. And the games could be, one game could be that if we wanted to do in the same spirit of this linkage, we could think about a system of equations. Well, actually, I'm not going to do it. I'm going to save it for next time. So I'm going to leave this here because we have plenty of time next time to do it. And it's easier just to do it in one fell swoop. But I think it's probably worthwhile doing this today. This is the essence of why we're attempting to do this. So everything we've talked about now are individual expressions. They don't interact with each other at all in these groups of hydraulic flow, chemical transport, heat flow, or mechanical behavior. And if you think about what the relationships are, they all inhabit the leading diagonals on these in this kind of grand scheme matrix equations. These individual equations are individual matrix equations within this bigger matrix. But as long as they exist only on the leading diagonals, then they don't interact with each other at all. The essence of what we'd now like to do is to figure out exactly what these coupling matrices are that exist on the non-leading diagonal terms. And once we're able to do that, we have enough to be able to couple things together, such as in thermomechanical behavior, hydromechanical behavior, thermo-hydromechanical behavior, and thermo-hydromechanical chemical behavior, where we introduce the different couplings. And so the couplings that we're talking about, and I guess there's another useful distinction to chat about, the couplings that we're talking about are purely physical interaction couplings rather than changes in material properties. And so both may be important, but the ones that we're talking about right here are that displacements and pore pressures are intrinsically linked because a change in fluid pressures will change displacements, and a change in displacements if you constrain the fluids from escaping, will change fluid pressures. And that's just a direct physical interaction between these. And that's separate from the fact that if you change deformations or fluid pressures, you might also change the physical properties of these systems, such as permeabilities or porosities, which might impact some of the other interactions, the couplings between them as well. And so it's worthwhile thinking about this division between coupled behavior where the physics of the systems are coupled, which is really what we're talking about in terms of this big relationship that we're talking about here. In addition to this, there may be behaviors that you stress it, you crack it, you change the permeability of it, and therefore all of a sudden as applying deformation, you're changing the permeability of that. But that's a very different thing from what we're trying to represent in this matrix relationship. So this just represents the physical interactions. If there are changes in material properties, then within this conductance matrix here, and we know that this conductance matrix looks something like integral A transpose dA dV, right? We know that these are the shape functions, so those won't change, but this is Darcy's law. And so if permeability changes as a function of applying a deformation, then all of a sudden this value will change and the terms that make up this matrix will physically change. But that's different from the fact that these matrices, when you add linking parameters on the off-diagonal portions, will also influence each other. So it's worthwhile keeping that straight. Direct interactions, which is this matrix, and also changes in properties as a result of